Using tangible objects is challenging in VR as error is inherent to tracking systems. Any position error might break the real and virtual contact's concomitance. We propose to instrument the tangible object with capacitive sensing. As the user gets closer, the capacity made with the electrode increases. The conditioned signal provides information on the distance of the user. This information is then used to retarget, prior contact, the fingertip's position from a standard optical tracking system, and attain better synchronization between virtual and tangible contacts. We correct the virtual height by interpolating the height estimated by the capacitive sensor and the optical tracking system. At far distance, we only use the optical tracking system, while at close distance, we only rely on the capacitive sensing. In order to maintain the virtual contact for any orientation of the hand, the retargeting is applied to the virtual point of the fingertip, which is the closest to the virtual surface. The setup is made of 7 Vicon camera and 2 HTC Vive lighthouses. A tangible object is instrumented with 3 capacitive electrodes on its top, back and right faces. The user wears a Vive tracker on the back of the hand, and 3 reflective markers on the back of the right index fingertip. Only one tracking system is enabled at a time. Here, the Vive tracker is disabled. We only track the fingertip using the Vicon. The following sequence shows the consequences of a common calibration error. As the user touched the tangible cube, an exaggerated gap remained between the virtual fingertip and the virtual cube. Now, with the same calibration error, we add the capacitive sensing. As the user touched the tangible cube, the virtual finger is retargeted toward the surface of the virtual cube. Here, the Vicon is disabled, the back hand is tracked using the Vive tracker, while the index is unconstrained. The following sequence shows the consequences of tracking the back of the hand and not directly the fingertip. The rigid virtual hand keeps moving through and away of the virtual cube as the user bends his finger with exaggerated movements. Now, whilst the finger is unconstrained, we add the capacitive sensing. Despite the user touching the tangible cube with various hand pose, the virtual contact always occurs. In the general case, while relying only on an external tracking system, additional mismatches can occur due to miscalibration or modeling mismatches. As a result, the virtual contact is often broken. As the user rolls his fingertip against the surface of the tangible cube, the virtual contact is not correctly maintained. By using the capacitive sensing, we can compensate any vertical error, and synchronize virtual and tangible contacts. Moreover, the contact with the virtual surface is maintained for any orientation of the virtual hand. To evaluate our approach, we conducted a user study enrolling 18 subjects performing 2 tasks. First, a touching task, where users had to touch the surface at the center in a natural and consistent way and hold the pose for at least 3 seconds. On this example, a user is performing the touching task on the top face of the cube. Then, he rates the coherency between real and virtual contacts on a scale from 1 to 7. Second, a tapping task where participants had to tap 10 times on the surface with various part of the fingertip and regularly at the center of the square. On this example, a user is performing the tapping task on the top face of the cube. Then, he again rates the coherency between real and virtual contacts on a scale from 1 to 7.